So the process with Starling cycles actually started with an engineering conversation. We looked at the bike, tried to decide where there was an opportunity to use generative design to achieve part consolidation and improve performance and reduce cost. Then we had to re-engineer how the new component was going to interface with the remainder of the bike. That produced these geometries that we have on the screen here. These are just the interface components from the larger assembly we saw in the introduction. So these have been modeled up and imported, and I've already set up a generative study. So we can see the preserves in green. Those are the parts of the space that we want to keep in the final design. The red obstacles are areas that we want the generative solver to not produce geometry. And I've also incorporated a series of materials. I've chosen some materials. I've produced a couple of load cases, and we're ready to run this as an unconstrained solve. What we want to do, though, first is adapt this setup for use with 2.5-axis machining constraints. So to access that, I'll go edit the manufacturing element in the design tree. And we'll go in here and see that we've selected unrestricted and milling manufacturing types, but the milling type is 3-axis. I'm going to leave that 3-axis alone and add a new configuration under which I'll select 2.5-axis. At this point, we need to answer two questions for the generative design tool. The first is the tool direction. We have to think quickly about how we're going to place this part on the body of the machine to manufacture it. I'll talk more about that in just a second. But I've selected Z, which happens to correspond to the axis of the holes in my preserved geometry, as well as the other fine features can be machined from the Z direction. We also have to say something about the smallest tool diameter we're going to use. At this point in the design process, we don't necessarily know what all our tooling looks like, so we'll keep the default at 10, and we'll also add another configuration with a smaller tool diameter just to get some sense of how much the designs change depending on the size of the tool. So I'll click OK to accept that dialog. Now I'm going to pop out and talk real briefly about what makes a good 2.5-axis generative setup. So here's an example. I've drawn some preserves here. This is a difficult setup because for a couple of reasons. First, we don't have one big open plane of the part. There's not a large top face that we can think about attaching to the machining table or using to cut away lots of material. We've got a preserve kind of floating up here. In addition, the preserved geometries themselves are difficult to machine. We'd have to do this with at least 2 setups, and I don't know about you, but I have a hard time machining square holes any day, regardless of how many setups I have. So we can improve this design for 2.5-axis by doing the following. First, let's rethink our setups. So I've decided that I'm going to approach this from the Y direction. So we'll cut it from the top like this. And now that I've made these changes, we can see that the exterior of all of our preserves could be cleanly cut from the top direction. We no longer have smooth curved surfaces we'd have to deal with. In addition, we'd add some obstacles to preserve those interior holes and keep them from being filled in with geometry during the generation. And for 2.5-axis in particular, we also have to provide obstacles above and below our preserved geometries because the generative solver gets confused when it has to decide whether or not to put material on top of the preserved geometry that you've already provided. So this is an example of we've taken that initial generative setup that really wasn't very well adapted to 2.5-axis, and we've made all the modifications we can, short of moving this top preserved body down to produce a really much more viable outcome. Note that the obstacle regions don't have to be 2.5-axis machinable. We can have these circular obstacle regions, and they'll be respected in the final design. Okay, back to our main part, back to the Starling cycle story. If we switch back to the design tab here and look at our obstacles, we can see first off that the obstacles that we've created conform perfectly to the preserves. So there's no gaps or space between the preserves and the obstacles above them. That's really important because we want to make sure that there's no opportunity for generated geometry to get stuck in the middle of these features that we have other plans for. What isn't quite there yet is not all of these preserves go all the way through the design domain. We need to make sure that the preserve cylinders, that the preserves the preserves and obstacles form an extrusion from the bottom to the top of the design space. To do that, I'll use the extrude command and grab these two faces, moving them up to the top of that preserve. Now this design is ready for 2.5 axis machining. We'll go back to generative design, and we note that now one of the pre-checks has been turned on, or two pre-checks warnings have been flagged. And they're telling us that as Fusion looks at this design, it's not sure that it's 2.5 axis machinable because some of the preserved geometries aren't clean extrusions that go all the way through the part. Clean extrusions are absolutely the safest way of doing this. If we had no geometry here and it was just a solid block, that'd be great, but the real world rarely affords us that freedom. So the rule of thumb that I'm giving you for the purpose of this class is you don't need to have extruded preserves, but when you combine the preserves and the obstacles on top of them, you need to have a clean extrusion all the way through the domain, just like these do. We're now ready to run generate on this solve, so I'll hit generate, pay my cloud credits, and go look at the results. In this case, I've already run this study, and I can come over to this other document and look at what we see. Generative design produces about 100 outcomes for this situation. We can page through them, and we did in the Stirling Cycles project. We went through all of these designs, looked at the different pros and cons and things we liked and things we didn't. I'm going to highlight just 4 using Explorer's compare view to talk through the differences and the things that we saw. I like to use the model view, especially when looking at 2.5 axis results. Maybe that's just because I'm a solver guy, but I think it shows the details of the part a little bit more clearly. It's not to say that you shouldn't use the design preview or the export preview before you export it. In the top left here, we have the unconstrained design. It's always going to be the most performant of the design options in terms of minimizing mass, and we can see that it achieves that through spindly, small generated geometries that would be very difficult to manufacture. The top right is a 3-axis solve. That's manufacturable. We talked about in the introduction, though, that it's not optimized for machining. You can make this, but you'll have to use a ball nose end mill and go back and forth and back and forth. It's going to be a little bit heavier than the 2.5 or than the unconstrained solve, but gives the designer more freedom than with 2.5 axis. The bottom shows 2.5 axis results. On the left is the one with the 5 layers. So we can see 2 on the top, 2 on the bottom, and 1 in the middle. And the right is a single attack direction with 3 layers. As we look through the results, we really didn't like this design on the left, or designs like it. There were quite a few, for a couple of reasons. One is that this thin member in the middle is going to not resist buckling very well. It'll also not resist the machining forces that will be imposed on it during manufacturing particularly well. So we didn't like this tall, thin wall. On the right, we did like this triangular shape, but again, we'd like to get rid of that tall, thin wall. These designs are also a little bit on the spindly side for what we would wish for in a design for a part like this. It's not going to work well for off-axis loads we haven't modeled and general wear and tear and fatigue. So our engineering judgment says we need to make some changes. That's fine. This first generative solve had the purpose of exploring the design space, trying to help us understand what the options were. We'll go back to our generative setup and make a couple changes to make this better. The first is we're going to introduce a starting shape. The starting shape is going to be really thin in this sort of central area of the design to discourage tall, thick walls from being formed. We'll also make a couple other changes that I'll show quickly. We could go back into the design workspace, model up our starting shape, and then come back into generative design and update the study. But that's going to invalidate this previous study because we've changed the geometry. So it can't guarantee us that the outcomes match the setup anymore. To keep from doing that, we're going to use the Edit Model Workspace. The Edit Model Workspace, which is inside Generative Design, lets us create a sandbox model for each of the generative studies that we want to run, for groups of generative studies. We've already got one generative model, which was automatically created and which we used for the study that I showed previously. What we'll do in this case is we're going to clone that generative model. We get to take the study along with it and keep all of its settings and constraints. And now we can make modifications without affecting the original generative model or the original part geometry. So what I'll do is I'll come in here and draw a sketch around the preserved geometries, just really quickly and roughly to give us some sense of what's going on. I've already done that. Here's the sketch. This literally took me less than 5 minutes. I just projected, drew some lines, threw it together, and then I took this and extruded it. where do we go? Let's go back into edit model. Okay, I took this and extruded it into 3 different layers. In the central section, we can see that it's much thinner, and so that should encourage a thinner, stockier structure to be produced instead of the tall, narrow walls. I've also changed the height of the geometry down at the bottom based on the results that I saw in the original generative run. I can finish edit model here and point out that I've made a couple of other changes. I established this as the starting shape. I also came into the into the objectives area and switched from an unconstrained minimize mass solve to a mass constraint, where we're trying to hit a target mass of 1/4 kilogram for this part. That came out of the sense that the designs that were being produced were a little bit too small, a little bit too spindly to hold up in the real world. So 1/4 kilogram was a little bit more than what we saw in some of the designs we thought were too small. Finally, I've added 2 additional load cases to this space. And these loads exploit different loads on the part we hadn't considered originally, and will encourage that triangular structure that we liked in some of the results. So again, I've already run this generative study, and we can jump straight in and look at the results. Quick tidbit about timings. I ran the first study, checked on it in a couple hours, and had enough results to get a general sense for where things were landing. It wasn't complete yet, but it was good enough for me to make some tweaks and launch the second study. The second study I ran overnight, so I started it, went home, came back the next day, and had some results. Again, we looked through all of these in the Starling Cycles project, but I'm just going to highlight a couple, or I'm going to highlight the same 4 and show how things have changed with the change in setup that we've done. Again, I'll show the model view, or maybe even the stress display view. I did these in the wrong order. In the bottom right is the unconstrained design. We can see that it's a little bit denser. It's hit that mass target and stopped. It also has more interlinking webs, which is a result of the additional load cases that we applied. Bottom left is the 3-axis. We're definitely seeing the triangular shape that we tried to encourage. And then on the top, we see the impact of our starting shape, which really caused it to not produce these tall, narrow walls, and instead we have a lower, flatter structure that'll be much easier to machine. It'll resist the machining forces better and should hold up better in the long term. We sorted through all these designs and picked the one we liked best. It turns out this one on the top right was our favorite choice, so we went into that one and clicked Create New Design from Outcome. So that produces this design here, which is the final outcome of the generative process. This is really cool too, because this isn't just an STL mesh or a T-spline. This is a series of sketch extrudes. Let me walk you real quickly through the timeline down here at the bottom. First, we import the preserves and obstacles from the original generative setup. Then we'll come in and create a sketch and an extrude. That generates the geometry for the first layer. Sketch extrude gives us the second, sketch extrude, the third. There's the extrude at the bottom now. And we can see that this just slowly builds up the geometry that we want to create. Finally, there's 3 combines. The first merges the layers into a single geometry. The second subtracts out the obstacles. And then finally, we union in the preserves. Okay, so we've got our generated geometry. What are we going to do with it? Well, we look at it and say, I'm not sure that this is really where I want it to be quite yet. For example, there's some wobble along this wall. The wobble not only isn't very pretty, it hurts our aesthetics, but it's also going to slow down the machining time because we have to move the tool more slowly when we're cutting corners. So we'd like to turn this into a nice, straight, smooth feature. In addition, from a perspective of performance, we think that there's probably an opportunity to improve the buckling performance in this design. Remember, buckling isn't normally incorporated into the generative design process. By extending these walls upward and downward to form a complete closed pocket around the design. We could do that in a couple different ways. We could just start over, and sometimes if we need explicit dimensioned geometry everywhere in our design, if that's our application, that may be the best thing to do. We can take this geometry as an idea, trace the geometry over with our own sketches, with our own primitives, and turn that into the final part. Alternately, because this is a full parametric geometry, we could edit the features. We could take what's already there, the sketches and extrudes, and modify the sketch geometry to fit our own purposes. Finally, A third way of approaching this is to keep what we have, but because it's an intelligent solid, it's a first-class geometry, we can go on from there and add new features to the timeline, add new extrudes, delete faces, rearrange things till we get the behavior that we want. We wound up using the edit features approach for this talk, partly because we wanted to show off what it could do, and partly because it was a good match for Starling Cycle's needs. The result is shown on the right. We see that we've got nice straight edges where we should, the pockets go all the way from top to bottom, or the walls go all the way from top to bottom, and we've smoothed out a lot of the wobbles throughout the design. So what I want to do is walk through, just in brief, rough strokes, how this process happens. Because it's not always, it takes about an hour for me to edit this design. It's not instantaneous. I need to go one further. But I want to get you some sense of the tools that we use and the thought process we have. First, we'll work on cleaning up this spline. Typically, I find that the generative outcomes have a little bit too dense a spline structure for my liking, so I'll come through and delete a lot of these redundant points. Ooh, I skipped a step. Never mind. Stepping back. Before we make any of these changes, I want to make a backup of the original shape so that I have some sense of how far I've drifted from the design created by the optimizer. So to do that, I'm going to take the body and copy it. There's copy. And then I'll create something called a base feature. It's down here towards the bottom. And what it lets us do is create geometry that is isolated from the rest of the design in terms of design history. It's not dependent on any of the sketches or extrudes or other features that have come before. So in this environment, I'll go ahead and paste. Click OK to accept the command and finish the base feature. Now if we look in our tree, we can see that we have two different models that are just perfectly overlapping because I haven't made any changes to the sketches yet. The second one, though, is from the base feature object, and because it's historyless, I can move it all the way back to the beginning of the design. I'll also rename it Original Shape so that it's easy to refer to later. Okay, now let's move back and pick up where I left off. We're going to edit this sketch, hide that original body, and again, go through and work on deleting some of these spline points to clean up this curve and make it prettier. What we can do to assist this and to get our curvatures nice and smooth and continuous is in the right-click menu, there's a toggle curvature display option. This is specific for spline curves within sketches, but it gives us some sense of the envelope of the curvature for this part. It'll update as I tweak things, and so I can use it to try to make the curvature envelope fairly uniform through the smooth, sweeping curves that we need to consider. I'll clean up that top section in a second, but I'm going to turn this off for now. We'll re-show our original body to see how much we've drifted from the design intent. Looks like I can pull that edge in just a little bit. Okay, up top here, I've got some bumps that I really don't like the looks of, so I'm going to go through and delete those. And I'll merge these two spline edges back together to form a closed profile. But now I've got a cusp here. I'd really like those to be tangent. I could use the tangency constraint, but it turns out that that slows fusion down quite a lot. What I'd rather do is look at these control polygons and make the first the first edge of each control polygon parallel. That'll enforce tangency for this kind of spline. So I can use the parallel constraint, grab those two edges. Now I've got a nice continuous curve again. Again, we're going to go through and delete some of these extraneous bits of geometry, smooth things out. Try to keep my spline points roughly evenly spaced. That makes for nice clean designs, and so on and so forth. I'd continue this around the remainder of the arc until I was happy with this profile. But for the purposes of this exercise, let's go ahead and move on. I'm going to hide the obstacles. There we go. So moving on to the next extrude, now I've created the next sketch. Now I've made changes to the sketch above, and the geometry that used to line up perfectly now doesn't. So the best practice that we've come up with for this is to actually grab these sketch faces and delete them, and then project, which is in the Create menu, Project Include, Project. We'll project that face down onto this sketch. This gives us an associative Whoops. Okay, we're going to try that again. We're going to project, but I forgot to turn on projection link here. So that'll create an associative relationship to the part above. And so now when I hide 16, I can see that we've got this, it's projected, we've got a constraint on this, and all that's left is for us to connect the geometry that's specific to this sketch to reclose those profiles. I can tell the profiles are closed when the sketch turns blue when I hover over it. I'm in sketch, right? Not quite sure what's going on there. Anyway, I've made those changes. Now what I'd like to do is add that rib that we talked about, that wall along the right-hand side, just by way of illustration. Now, unfortunately, the geometry that contains the spline for that is on the next layer down, which I can't see in the timeline. What I can do instead is use my handy reference body, my original shape, and I'll project just this face from the original body. This time, though, I'm going to uncheck projection link so that I get an explicit copy that doesn't have any of the associativity to the original body, because I don't need it. I want to make changes to this one. Now, these could be a straight line, but it's a spline curve with wobbles in it. Let's replace it with a line. To do that, I'm going to use the line command. I'll start by drawing a construction line that crosses the original just a little bit, and then I'll go parallel to the original down to about the point where I want it to stop, which I think should be about here. One more construction line, and I'm done drawing geometry. Now I'm going to grab my new line and drag it a little bit further out of the way to make it clear what's happening. I can use the trim command to get rid of, oh, I have two of these on top of each other. That's fun. Pardon me a second while I clean this up. Okay. There we go. So I've trimmed away the geometry that was in there, and then I'll put the line back where I wanted it. We'll check the original body to make sure that that line hasn't drifted out of where we want it to be. And then before I connect it, because this is not quite lined up with the spline yet, I want to adjust the spline to make it line up and be tangent. But before I do that, I'm going to fix the endpoints of this line so that it doesn't move in this next step. So we'll snap the endpoint on. Again, we're going to grab the parallel constraint and make that first element of the control polygon parallel with my curve. I'll do the same thing up here. Take the first element of my control polygon, make it parallel, and then add a coincident constraint. There we go. Let's delete our construction geometry. We don't need that anymore. It was just to make it easy to trim. And we'll add an offset. We'll take this curve and offset it to produce the other side of this wall. That's unhappy today. Down at the bottom here, we're going to delete the spline we don't need and do the same process of merging this straight line after I fix its endpoint in with the spline. Grab our parallel constraint, snap it, and be done. Up top, I should have had a geometry that offset, but for some reason it didn't. Looks like there's something confused up here. So what I'll do is just leave it for the purposes of today. After I finished editing this sketch, here's what things look like. I created the wall on the left side, did the same thing, or on the right side, I did the same thing on the left, and then came through and added this fillet or this curve to complete the profile. So now I have a nice complete profile that I'll use for this layer. And then when I get to the next layer down, I can just grab these edges and project them exactly as I did back at the beginning. So we'll finish sketch, and I'll move forwards to the end of the timeline here we see the shape with all of the sketch edits done. So I've now got the nice straight edges that I wanted. I've replaced that spline circle-ish thing with a real circle, and everything is pretty much there. There's still a few tweaks to do, a few touch-ups, which are the same touch-ups that you do anytime you're getting ready to run a model through CAM. We'll go around this profile and fillet any sharp corners that we find, check the curvature, or sorry, check the radius. And we also did a design iteration at this point in the process where we discovered that the preserved geometries we've made weren't as manufacturable as we thought we were, so we went back through and tweaked them and didn't regenerate the solve. We just made modifications to the preserves by adding features to the timeline. So this one is now all ready for CAM. I forgot one bit of my geometry, or one comment. Back when we were modifying, adding a line, we replaced a part of the spline with a line. It turns out we can do the same thing for arcs. So we can take a spline arc, put a real arc on top of it, trim away the spline, and have the arc take its place. The procedure is exactly the same. The handout describes how to do it. Okay, with that, we'll turn it over to Chris to talk through the demo on CAM.